Bonsoir Montréal-Python. Good evening Montreal-Python and welcome to Montreal-Python 99, Nez Vigilant, Vigilant knows. Our program for tonight is going to come in just a moment, but before we get there, I need to manage to advance my slides and I need to tell you that you should join us on Slack. And the link is right here and it's also in the description on YouTube. And if you join us on Slack or if you decide to comment on YouTube, know that we have a code of conduct at Montreal-Python. That is very simple. It basically says that we should all be excellent between one another. Alors, avant que je passe au programme de ce soir, je veux vous rappeler que vous pouvez vous joindre à nous sur Slack. Et vous avez le lien ici sur l'écran, à l'écran. Et dans la description du vidéo sur YouTube. Et puis, si vous décidez d'interagir avec nous, soit sur Slack ou dans les commentaires YouTube, eh bien, on a un code de conduite à Montréal-Python. Puis, c'est super simple. Ça dit qu'on devrait être excellents les uns envers les autres. Si vous voyez quelque chose qui ne vous semble pas excellent, bien, trouvez-moi. Moi, je suis Yannick ou Duc, qui s'appelle Duc sur Slack. Et dites-nous-le et on va se faire de notre mieux pour régler ces problèmes. Alors, notre programme pour ce soir, on va en premier avoir Duc qui va nous faire un résumé de notre premier événement qu'on a fait en personne depuis la pandémie. On a eu une journée de programmation samedi passé. Et Duc va nous en parler. Et puis ensuite, Nicolas, il va nous parler de comment adresser ou comment utiliser Python pour résoudre des problèmes difficiles. So our program tonight, Duc is first going to give us a little summary of our first in-person event that we had last Saturday. We had a programming day. And then Nicholas Nadeau is going to tell us about harnessing Python for solving hard technical applications. And then after that, we're going to have our traditional virtual happy hour on Jitsi. You can come with whatever drink you feel like drinking. It doesn't have to be a beer, but if you do drink a beer, you might be in good company because there's a fair chance that I will have one. Other than that, keep looking at our page on Meetup. It's Montréal-Python, and we list all of our events there. We list them also in a couple other places, but we're less regular in posting elsewhere. So Meetup is definitely the place to keep an eye on. Alors, autre chose à mentionner, eh bien, on a notre page Meetup sur laquelle on affiche tous nos événements futurs. Ça arrive qu'on les poste ailleurs, comme sur notre page LinkedIn ou Facebook ou même sur la mailing list, mais on est un petit peu moins assidu là-dessus. La page Meetup est le meilleur endroit pour suivre nos événements. Et puis, j'aimerais remercier FGNR qui va hoster notre 5 à 7 virtuel ce soir. Et puis, il y a Eddie qui a pris cette magnifique photo du serpent bleu. Alors, merci Eddie de partager cette photo magnifique. Et sur ce, je vais inviter Duc qui va nous parler de la journée de programmation. Bonjour Duc, comment ça va?
Hey, salut Yannick. Oui, ça va bien et toi?
Ça va super.
OK. Mais j'imagine que je me lance. Mais c'est ça, c'est que comme Yannick a dit, on a eu notre premier événement en personne depuis je ne sais pas combien de temps, je pense que même plus, ça fait tellement longtemps. Mais c'est ça, mais vous avez bien le contexte. Mais c'était pas mais c'était une journée de programmation que on avait 3 groupes qui sont l'introduction à programmation en Python et analyse de données plus intelligence artificielle. Et aussi, le 3e groupe, c'était développement web avec Django. Malheureusement, c'est sûr que t'es comme plus qu'il y a du monde, plus que c'est plus le fun, mais on n'a pas eu tant de personnes qui sont venues comme qu'on voulait. Fait que la prochaine fois, il va falloir que vous contactez vos amis ou votre famille et tout ça pour venir nous encourager puis apprendre à développer avec nous. Et tout ça, on a eu 4-5 personnes dans le groupe d'introduction à programmation Python et aussi 5 personnes dans intelligence artificielle et une personne dans le développement web avec Django. Fait que, c'est ça, puis c'est sûr que on va vous annoncer, si jamais on fait, on va encore toujours annoncer, mais on cherche aussi des places pour qu'on peut, parce que là, on a fait l'affaire avec l'Université de Montréal, avec l'équipe de Érudit qui nous a hosté, qui nous a prêté les locaux et tout ça. Fait que merci à Érudit. Mais c'est sûr que prochainement, si votre entreprise ou votre organisation veut nous hoster, si vous avez comme des petits locaux, qu'on peut faire des petits ateliers comme ça, on est toujours, comment dire, enchanté à aller faire ce genre d'événement. Le feedback que j'ai eu, c'était très positif. C'est ça. Fait que c'est sûr qu'on va refaire ça encore et encore, mais on va voir. C'est bon. Fait que, mais restez en contact là, comme tous les canaux de communication que Yannick a mentionné tantôt. C'est sûr que si on fait d'autres événements, mais on va republier toutes ces informations sur ça. Fait que je pense que c'est pas mal ça de mon côté. Est-ce que Yannick, tu veux-tu ajouter d'autres choses ou?
Merci pour ce résumé, Duc. Est-ce que vous avez discuté, moi j'étais pas là, ça peut-être que ça paraît. Ouais. Est-ce que vous avez discuté entre les présentateurs et puis toi, quand pourrait être notre prochain événement de journée de programmation? C'est clair, perdez pas le fil, tout le monde. On va continuer de faire des soirées de programmation en virtuel, comme on a fait toute l'année passée. Mais on veut commencer à faire plus d'événements en personne. Donc, selon toi, Duc, quand est-ce qu'on s'enligne pour notre prochain événement en personne?
Prochain événement en personne, moi, je dirais, moi, c'est sûr que j'aimerais ça que ça soit fait dans 2 mois. Mais d'après, c'est sûr que là, quand on fait un événement comme ça, c'est toute la journée. Puis aussi, c'est toute la journée de samedi, ce que, selon les organisations, selon nos collègues, c'est peut-être un peu trop pour eux parce que c'est quand même toute une journée de samedi, là, on s'entend. Fait que on va sûrement se rencontrer et discuter de ça. Ouais. Mais c'est sûr que oui, c'est vrai que si on n'est pas capable de faire en personne très souvent, mais comme tu l'as dit, notre journée de programmation en ligne qui se fait un peu plus facilement pour nous, ça va être une bonne alternative aussi.
C'est super ça, Duc. Merci beaucoup pour ce résumé. Et puis, j'invite tout le monde à suivre qu'est-ce qui se passe sur Meetup parce qu'on va annoncer le plus tôt possible quand va être notre prochain événement de programmation, soit une soirée ou soit une journée en personne. Et sur ce, je vais inviter Nicolas. Nicolas, qui est docteur Nadeau, en fait, qui est fondateur de Nadeau, je l'ai oublié, Nadeau Technologie, Innovation. Nadeau Innovation, c'est sur l'écran. Ben oui. Qui va nous parler un peu de ses expériences en utilisant Python pour résoudre des problèmes techniques difficiles comme le design d'équipements biomédicaux, l'imprimerie 3D haute performance, je ne sais pas ce que ça veut dire, mais il va nous en parler. La robotique et l'intelligence artificielle. So our next speaker is going to be Nicholas Nadeau, Dr. Nadeau, who is a founder of Nadeau Innovation, and he is going to tell us a little bit about his experience using Python for solving hard technical problems such as biomedical equipment design, high-performance 3D printing, robotics, and AI. Nicolas, je te passe la scène.
All right. Thank you very much, Yannick. Thank you very much, Duc, for having us here today. So I'm Nicholas. Thank you, Montreal-Python, for hosting the event. So today we're going to be talking about harnessing Python for hard tech applications. And for me, hard tech is that interface between hardware and software, really where robotics, AI, edge AI, IoT, all these things really come together. And that's been essentially where I've spent most of my career. I don't do so much of the cloud SaaS side of software or hardware development. I'm really in the robotics side of things. And so the theme of my talk today is really see where Python fits into this hardware intelligence systems. And I'm going to use my career as examples and stepping stones because I find it really follows the progress of robotics and AI over the past decade or so and how it's evolved over that time. One thing I found early on in my career that I thought was missing was just simple applications where Python is used. As a young engineer, I would always want to know, where would I go to use these skills, these tools I enjoy a lot? Do I have to go to a Python only place, or can I explore other applications and domains and still bring in the tools that I want to use? And if we're just go by the internet, a lot of people might think that Python is only used for AI or web development, but there's so many more applications that we don't traditionally think of. And from a diversity, equity, and inclusion point of view, I want the world of robotics, AI, IoT, edge applications to bring in the skills of non-hardware, non-hard tech people, and really bring in these super useful perspectives and people into these applications, making it accessible to everyone of all backgrounds and skill sets. So that's essentially what this presentation is going to be. So a little bit about me. Currently, I am helping companies build next generation technologies and empowering high performance teams through fractional CTO services. So that's Nadeau Innovations. Most recently, before that, I was the CTO of Haloti Robotics, a global humanoid robotics company. Before that, I was the head of engineering at Aeon 3D, doing high performance 3D printing out of Y Combinator. I spent the last decade or so creating unique technologies for biomedical applications, food robotics, humanoid robotics, Industry 4.0, additive manufacturing. I'm a PN and member of the Order, did my PhD at ETS where I mixed, and that was really where I first started mixing the machine learning, the AI with robotics to do medical ultrasound. I once upon a time was originally a mechanical engineer out of McGill, and that's really where my love of hardware comes from. And most of the time you can find me as a mentor at Techstars, Next AI, Career Destruction Lab, and Founder Fuel. So first application, let's get to the fun stuff. Over a decade ago, I had the opportunity to work with a small biomedical engineering company here in Montreal called Rogue Research. Had a lot of fun, great team there, really focused on high risk, high reward type projects, those moonshots. And we developed devices and tools for brain imaging, cognitive neuroscience, and veterinary research. One of these devices that we created was one of the first semi-portable near-infrared spectroscopy systems, so NIRS, that we pushed on the market. And so NIRS is a non-invasive technique and method used to measure brain activity. It's often used in brain imaging studies to help researchers understand how the brain functions, what parts of the brain light up when you do different activities or do different cognitive neuroscience tasks. And one of the advantages of NIRS is that it's non-invasive, meaning that it doesn't need any surgery or injection of anything into the body. We really just put a cap on a person's head. And so it's less sensitive compared to other techniques like MRI. We can do it with motion. We can use it on young children or patients with movement disorders because you don't have to stay perfectly still, which is a lot of fun when you're doing like cognitive neuroscience in sports, for instance. Now, one of the most critical parts of a NIR system is the opto design.
Nicholas, please pardon me to interrupt. I think we might be able to play a little bit with the layout of your screen to better use the screen real estate. I see you're getting into the busier slides here. Oh, that's so much better.
There we go.
Let's
zoom in. Perfect. You know, you try to do the multi-monitor view. All right.
Very good.
So opto design, so NIRS essentially works by shooting lasers into people's heads. They're low powered lasers in the infrared spectrum, and the light actually passes through the scalp and skull into the brain. And so when the light enters the brain, it interacts with the brain tissue, the hemoglobin in the bloodstream, which carries the oxygen in the blood. And by measuring the way the light interacts with this hemoglobin, we can learn how different parts of the brain are activated or deactivated and where oxygen is being delivered to different parts of the brain. And this gives us insight into which areas of the brain are more active. And so from a design engineer perspective, this is a fiber optic cable glued to a mirror prism glued to a lens. And this allows us to get like a nice low profile 90-degree optode, but there's a lot of mechanical optimizations that need to be done. And that all had to do with how the light actually passes through. And so this project was actually my start into Python over a decade ago when I was just a young mechanical design engineer. And so coming out of university, I thought MATLAB was the greatest thing ever, but I soon realized that without all the expensive toolboxes that the universities give you for free, MATLAB is essentially useless. And so that's where I started with Python. We needed to optimize the optode's fiber optic and lens design to know how the assembly and the mechanical tolerances affected the light emission and the detection performances of the source and detection optodes. And so I designed a simple 2D ray tracing optimization tool that simulated the laser rays and the attenuation of the laser light using Monte Carlo methods, essentially using randomized statistical methods to shoot out a whole bunch of laser photons and try and guess which ones make it to the end or get detected on the way back. And so they would all get different starting parameters. Essentially, I'd build a table and many database of laser rays that go out, how many were detected, and then randomize around how the different mechanical assembly methods would affect that performance. We were then able to visualize the rays with matplotlib, and so I get to share the results with my stakeholders for design reviews and the non-technical people. From there, what's a lot of fun is we can export everything to SolidWorks as 2D layups, into sketches as Excel-driven design parameters with SolidWorks, and that let me basically auto-generate a lot of the mechanical assemblies and mechanical parts that I then get to build and test and compare those values and that performance back to the simulation. And so it was really this Python in the loop with hardware design that really started my love for this, easy to use but super powerful language. After Rogue and out of Y Combinator, I had the opportunity to be head of engineering at Aeon 3D. And so this is Montreal's super awesome 3D printing company. We did a lot of aerospace and biomedical applications. Essentially, a 3D printer is just a robot in an oven. And from a systems perspective, we treat it as an IoT device. And so this let us bring in a lot of tools and techniques from the IoT world in order to make this a much more smart system, if you will. One fun application is that we have the first 3D printed parts landing on the moon quite soon with the Astrobotics Peregrine moon lander. I believe it's landing at the end of March. And it all starts, so being able to build these high performance systems and service these high performance clients with these top end materials that are very hard to control and design around, we need a system that's easy to use, agile to develop on, and outputs reliable parts. And the developer and research experience, really that UI, UX, that workflow of the system is key to making something like this successful. So let's look at the actual tech stack that went into designing, a 3D printing IoT type system like this. The HMI is essentially a web app. Anyone familiar with full stack web development would instantly be able to develop on our system. Even more fun was that the infrastructure took advantage of Docker containers, so we could do over-the-air updates, OTA, on the fly, do A/B deployments, roll out our different firmwares and softwares to our internal machines, to external clients, to special clients, do a lot of remote diagnostics and logging. All of this is just standard in the SaaS where we brought it over to the hardware and, sort of like hardware as a service type thing. And so the UI UX was just a React front end. You can see an example there on the left, just a nice touch screen with big buttons. The back end was a Python Flask container, so that gave us all our endpoints that we needed to do. And then down at the firmware level, it was just C++ firmware on an 18 megabase microcontroller, and that would control the motion system, the thermal system of the 3D printer. I had a lot of fun using Balena as our fleet management infrastructure as a service. So this let us do remote management of the machines, update machines, A/B deployments. Anybody who's ever done any form of Docker container deployments in the SaaS world, whether through like GitLab, CI/CD, and whatnot, will be very familiar with this workflow. And this really lets us do a separation of concerns between the hardware engineers and the people who needed that hardware expertise and the other types of developers that we were able to onboard and bring into the team. And it opens the doors to non-hardware people to be able to contribute to our system. And honestly, it made hiring a lot easier. And so, like all robots, especially robots inside of 200-degree ovens, debugging and customer success were super important. In robotics, things will break, and you have to be able to quickly respond to the event and fix it. And so we had a lot of clients at secure aerospace facilities where the word cloud essentially scared them, and everything had to be on-prem. And so the alternative solution is to dump all the logs into a zip file onto a USB key, which is it's a real pain. And USB keys in secure facilities are a security issue in and of themselves. So we assumed that everyone had access to a phone camera, and we had the cool idea to use our nice touchscreen display, which was nice and big, to display QR codes with all the basic log data inside of it embedded as a JSON. And this let us really help customer support and make the process of something going wrong in the field, customer interacts with our system, to being able to connect with our customer service team, provide them all the information that they would need in order to resolve that ticket or that issue much more quick. Bringing agile to that customer success process. And so instead of Jira Service Desk tickets being filled with I think this, I think that, a couple of drop downs, we're able to attach a picture of the QR code with embedded in all the basic logs that we need to debug the issue faster. And this led to a better customer experience, better developer experience, because we're able to, go quicker, and developers get frustrated sometimes chasing after the information from the end user. QR codes were able to also allow our users to audit what data was being sent. So we were very transparent with our data collection relationship with our end users. And so all of this was just a few lines of Python. You could see here, essentially, on the left, within our Flask app. The touchscreen would just dump it all into a dictionary, and using the QR code Python library, in a couple of lines, basically transform into a QR code that were able to just pop up on the screen when you need to do a debugging situation. A lot of fun. This was a great, little quick thing that made the end-to-end experience a lot nicer. On the data science and AI side of things, whoever's done 3D printing before, hobby 3D printing with, Prussias at home, the struggle of figuring out your print parameters. There's nozzle speeds, nozzle temperatures, chamber temperatures, extrusion multipliers. All of these have an effect on your final print outcome, whether or not the print even succeeds or not, or crashes your toolhead, but also on the mechanical part properties, such as tensile strength. This is super important, these properties, to the design engineers in aerospace, in biomedical, where they need really consistent and robust results. And so the printer itself also has an effect on the part parameters. So we now have your parameters going in, and what printer you printed on that might have small effects on the final outcome. And so we want to start collecting data, build models, and have a better, predictive understanding of what things affected the part outcome. We collected basic logs using Balena and using your standard SaaS type apps and whatnot to feed it to logging infrastructure. But from an R&D perspective, we needed higher fidelity, higher resolution logging, and really at the scientific level. So fortunately, we had dozens of printers internally as part of our internal print farm, where we do a lot of prototyping, a lot of testing, a lot of customer success type thing. Since the machines were basically IoT devices with REST endpoints served by that Python Flask application layer, I simply set up a Python scraper cron job that collected this high resolution data over time. Now, a lot of people might think, well, you could just create a push service pub sub type thing to push to some external data store. But this simple infrastructure didn't need any external services. We're just essentially cron jobbing, scraping these API endpoints. And so that means any engineer, even hardware engineers with basically little to no software experience, were able to maintain and interact with this data collection system. And this is, typically a lot heavier data than you send to the cloud or your standard metrics observability stack. But these endpoints were also public to our research users who needed to use this data for their studies, for research papers, and things like that. So we're essentially also dog fooding our client tools at the same time. And now stakeholders were able to check out daily, weekly data summaries that were dumped as CSVs internally in our shared drive. So the Python cron job was just a REST API with a request that we're targeting. Pandas and SQL Alchemy were used for the ETL, dumped it to CSV Excel files into a shared, I think we were using Teams back at the days, probably a SharePoint, also sent to internal Postgres. And then we display it, pretty dashboards, and Grafana shows up all our uptime, different printers, different temperatures, things like that. And also a Metabase platform for our less technical users to be able to do more business intelligence, insight type questions and querying of the data. And so having this data collection system with the core being Python, really owned by the R&D team, operated by the R&D team, who wasn't necessarily, and this is the hardware R&D team, weren't necessarily, the top software people. They were able to be empowered as a team and enabled, better development experience, the ability to test new features and prototypes without having to then go over to the software team and get them to maintain their own, a separate set of infrastructure. onto some of the work I did during my PhD. So this is the world of pure academics and research. I started to directly combine the robotics and AI side of things over there. And this is really where I got into that deep hard tech world where the software controlled the hardware systems and made decisions on the fly. And the applications ranged from, robotics. Robotics. I made a robotics framework for Python called Pybotics. Presented that, I believe, at PyCon a number of years ago. I presented here at Montréal-Python, I think a few years ago, my real-time motion optimization. We did some calibration studies as well. And so I'm not going to dive into those ones too much since I've presented them already, but I just want to give a high-level overview where Python sort of comes into this robotics world. And so offline program is probably the #1 application I see. Super important when developing robotics applications because it allows engineers to simulate and test environment movements and tasks in this virtual environment that doesn't break, doesn't cost anything if you do break it. And this all happens before you implement it in the physical world where breaking things is very expensive. You essentially create a digital twin of the robot and test its performance, check for collisions, and optimize the movements and the trajectories without needing the physical hardware right in front of you. So it reduces damage and also makes it more efficient because you can do all this on your couch at home instead of having to have access to that equipment and turn off the production line just to do your tests, which reduces costs quite a bit. From an architectural point of view, you have essentially Python at the center of development these days. We have a core Python app that's agnostic whether it's controlling a simulated robot or a real robot. And now you get to connect. You just have a pointer going to whether you're pushing your application motions and everything to a robot simulator that controls a simulated robot or a real robot controller that's controlling a real robot. And even further, sometimes some of these simulators are able to also directly control the robot controller. And so this lets us do things like CI/CD with real robot applications because each code change can be tested in the simulated environment before being deployed onto the real one and to push to production where things can go really wrong if it's not tested. And so this was something I presented previously at Montreal-Python. I just want to reiterate that the tech stack of Python goes beyond just controlling the robots, really even doing the autonomy and training and data collection around robotics, around calibration, all that AI stuff that we're starting to see these days. And the biggest unfortunate thing is that every robot has its own software SDK or interface. And you have to basically make wrappers upon wrappers upon wrappers to control all these robots. And so that's where I love GRPC. Basically, it provides a language agnostic approach to wrapping all these systems and communications infrastructure. So my Python client at the center, where I do my business logic, can really interact with everything agnostically. It's scalable, it brings hardware in the root loop, it makes everything testable, makes mocking really easy because all these hardware devices essentially become abstract servers that provide a set of services or callable functions to my Python client where I do that business logic. The client doesn't need to know how anything works because everything is this black box defined through the protobuf files of what needs to be as an input and what's expected as an output. And now everything can stay versioned. All these interfaces are well defined and shared. It's an infrastructure as code approach. The protobuf files can now auto generate boilerplate communications, APIs and client servers essentially on the fly as needed. You need a Java endpoint, you can spin up a Java endpoint. You need, Node, you need Python. Everything is just given to you for free essentially. And so from a hardware engineering perspective, the experiment design and setup time is greatly reduced through this automation of, well-defined interfaces. So into my most recent work, several years ago, I met a bunch of Norwegians on the internet, and that's how Haloti Robotics really got started. And in the span of a couple of years, we grew to 4 countries, 5 offices, a new humanoid robot designed for security guarding. We grew to 50 plus employees, and we sold the biggest contract ever with 140 robots to ADT Commercial in the US. So that was a lot of fun, a lot of hyper growth going on, building 6-foot tall robots like this. And so we were big fans of autonomy. We really embraced the usage of, the large language models, the LLMs that you're hearing about now, techniques from the cutting edge AI research to bring them in to the robotics space and really train our robots end to end using just the vision data, that image data from our camera system on the robot head. So this is very sort of similar, if you think about it, to that paper and publication that was done many years ago, but AI playing the Atari by just using the image input and using controller outputs. But with robotics and the human environment, the real world, all unstructured, data collection is really hard. There's lots of corner cases. Human environments are really complex, messy, lots of soft, deformable objects. And so we really took advantage, and you can see this on the left here, of human-in-the-loop VR to let us take control of the robot in low-confidence situations. And this let us capture the human motions as expert data for the behavior cloning and imitation learning AI model training. And so on the left, we're just using an Oculus Quest 2 and Unity to drive the robot through some endpoints. From an architectural perspective, robots are really complex, and humanoid robots are even more complex. And the goal, as CTO there, so my goal was really trying how to make it as simple as possible to onboard new engineers, to make it a maintainable structure that can grow with the growth of the company. We wanted to make sure that onboarding was as straightforward as possible. We wanted to make sure that the developer experience and getting new ideas, new features deployed was as easy as possible. And so we split the architecture into 3 distinct layers: core, interface, and application. And this allowed us to create a separation of concerns, not only in the modules and the code base, but also in the skills and the development workflows and the types of engineers we'd be able to bring on board to really contribute to our platform. And so at the core layer, that's honestly the only place where you need deep robotics knowledge. And as you move up the chain through the interface to the application layer, pure ML people, full stack developers, non-roboticists really would be successful and contributing to the overall application. Python, hands down, is the primary language at the top layer. At the core layer, C, C++ is that real-time code. We RT-patch the kernel to really control our own scheduling. A self-balancing robot needs to stay up and you need to maintain that minimum latency in order to keep that running. But as you move up the layer, you don't need that real time anymore. And so you're able to use tools like Docker and containerize everything. OpenCV, Grafana, PyTorch, all of that was really that top layer in order to quickly spin up demos, be able to build end features and applications for our clients as quickly as possible. And containerization really helps that whole dependency management side of things, where engineers are able to spin up ideas and just deploy them as container without worrying how it affects other people's containers and applications. And so a great example of this was actually at an Industry 4.0 conference in Milan that we did at IPAC with one of our partners, Ultipack. So Ultipack makes machines in Bologna, Italy, that packages dried food goods such as pastas and chickpeas. And so like Barilla pasta and DiCecco products are key examples of what might be packed on one of these machines. And so they wanted a demo of potential factory of the future with robots alongside humans. And we didn't have too much time to spin this up. And so honestly, in the span of a few weeks, we put together, nice and containerized at that application layer, OpenCV, so the OpenCV Python module, QR codes, as you can see here, and Aruco markers for doing some of that triangulation of the manipulation side of things, and using ROS really as that communication infrastructure. And so ROS is really popular in the robotics world as a pub-sub framework. So nowadays, I've gone private, and I lend my expertise through fractional CTO services, and helping corporations, helping startups make the right decisions early on. And this lets me get to play with a lot of great tech and work with a lot of great people, more so than just one company at a time. And so one of my favorite clients recently, you might have seen this on MTL Blog or the Gazette or Radio-Canada, is Osidia, and they've been deploying the Spot robot for dynamic sensing applications. One of the big clients was the STM recently, featured in all our local media. And so the goal of this is, can we make the human world closed loop for sensing applications? Can the Spot robot live its best life, patrolling locations, collecting data, so that the backend systems, our stakeholders, our decision makers can make data-driven decisions? And so predictive maintenance using basic computer vision loaded onto a Docker container is all that's really needed to work with this robot. And it's a beautiful system. And so it's been one of my most favorite platforms to develop on lately. The robot just works. It could fall over, it'll get back up, it can go up and down stairs, go through doorways, navigate on its own. You don't have to focus on the debugging and fixing robots like I have had to do in a lot of other my companies or robotics applications when you build the robot yourself. And so instead of debugging robots all day, I could just focus on the end application and develop using standard developer tools and workflows. This makes it really easy to spin up new tests and demos for non-roboticists to succeed. And in this example, in this GIF here, this is a quick example Boston Dynamics gives of just using OpenCV Python again, NumPy, and TensorFlow loaded up into Docker containers to quickly teach the robot how to just randomly pick up objects that it detects through its camera system. And we're going to get into how all this works. So at the core, the Spot SDK is just a nice Python SDK. So pip install, I think it's Boston Dying-client, and you have everything you need to get started with the Spot. It's wonderful. So anyone who's worked with Python before, you'll quickly understand what's going on here. This is the Hello Spot application from Boston Dynamics. You start with some basic authentication and configurations of the robot, and then you connect. And now we get into, it might be a little hard to see on the big screen here. I'm going to try and zoom this in a little more. But essentially, we get into just moving the robot right away. And all of this is loaded into containers so that we can control versions, packages. We can use CI/CD to deploy things. We can do A/B testing. We can bring in our favorite packages like PyTorch, Pandas, NumPy, SciPy, OpenCV, Flask, all onto our robot without any complications because everything is nice and containerized. And so from an architectural perspective, Boston Dynamics apparently shares the same vision that I had sort of at Haloti, is that there's a separation really through three distinct layers of the robot. The core layer where, the Boston Dynamics is the only people to touch that layer, if you will, with the payloads and the base authentication and things like that. We have a robot layer that's sort of like the interface layer that really defines the state, the control, and the data. And these are like the objects that you pass up and down through the core to autonomy layer. And then their autonomy layer is really like my applications layer, where you get the missions, you get the docking commands, you get a lot of those services that the end user would want to interact with. And so it's sort of similar to the MVC model view control architecture we see in web apps, where the core model cannot be directly touched by the front end or the user. We have to pass through an interface type layer. And so architecturally, this is how that fetch application actually runs that you saw before in the GIF. So the onboard Spot robot computer runs a TensorFlow model alongside a person's laptop that acts as sort of like the client controller. And so the main script, that fetch.py script, is run off board from the robot, but then networks using everyone's favorite GRPC with the robot in order to communicate, go here, go there, pick up this, pick up that. Is this an object that I should pick up? Yes or no. And so all these Spot extensions are just wrapped in Docker images, so we can deploy new ones ad hoc as needed with the latest and greatest code, making the whole developer experience as seamless and efficient as possible, and also allowing non-roboticists to be successful. And so inside our Docker container in the robot computer, we just have our TensorFlow model running. And so anybody who's familiar with Docker looks at this and says, yep, we can get up and running with robotics. So if you've worked in the SaaS world before and web development, Docker containers, which is really nice, NVIDIA provides optimized Docker containers from their image repository. They're optimized for TensorFlow, PyTorch, and all those types of things, and really makes AI ML application development a lot more easier. We just pull and use these. And so these standard containers are able to be loaded directly onto the Spot and makes it easy for anyone to be a robotics superstar, honestly, without necessarily having that hardware or robotics background. And so what's next for the world of hard tech, robotics, edge AI? I honestly see a super bright future for Pythonistas of all backgrounds to get into these robotics and hard tech applications. The core layers of hardware devices, robotics, IoT, they're becoming more and more of a commodity, and they're stable. And like Boston Dynamics, the Spot robot is a perfect example of that, where we can buy a platform that just works And now the differentiating factor is we get to focus on the application, the outcomes. And this is really going to be driven by people with that business mindset, that user interface, user experience mindset, which traditionally, honestly, comes from more of a web development or traditional developer background, not necessarily, those roboticists or those hardware engineers. And so, honestly, if you know Python, if you know APIs, if you know Docker, CI/CD, databases, and have some basic hardware understanding, you're set up for a super successful career in hard tech right now, right at the point where things are starting to really kick off. Thank you very much.
Thank you, Nicolas. Let me bring Duke, who's going to lead our question period.
All right. Thank you, Yannick. Hey, thank you, Nicholas. Looks like you have a lot of fun at your job.
Yeah, I get to play with a lot of robots.
Cool. Yeah. Okay. Let me see. Okay. I would like to invite everybody to ask your question for Nicolas at or Slack channel, or you can write directly your on YouTube. Okay, I have already first question. What are the most common reasons why a simulated robot will not behave the same as a real robot?
So yeah, it's all about calibration. So a simulated robot out of the box, you'll have what's called your nominal model. So this is your kinematic model, how each, I'm going to use right-hand rule if anyone's done chemistry or mechanics before. You have each joint of the robot connected to the next joint. And so essentially you have different lengths and attachment points and angles between these joints. And really how that robot, the real robot, is assembled, screws are tightened, how gravity, how the temperature, how all your friction, all that affects these little micro tolerances in how the robot's affected. So while your nominal robot on paper is maybe 600 millimeters joint to joint, your real robot's going to be like 600.5 millimeters in the next joint. And all those errors stack up. So your simulated robot will behave essentially perfectly, and your real robot will be off by a few millimeters in the real world. And this is where calibration comes in. What you're really trying to do is close that error gap between your nominal model and your real robot, such that your simulation knows what the real robot actually is in real life. And so when you do this offline programming, you have basically a 1-for-1. But out of the box, all the big robot companies, KUKA, ABB, Fanuc, they'll talk about precision. I didn't put the slide up here, but there's a slide I like to show with the bullseyes and precision versus accuracy. Industrial robots are great at precision. They will go to the same place over and over and over again and always be at the same spot. Out of the box, they're actually pretty terrible at accuracy, and that's go to a random location accurately and hit that spot. So industrial robots will be precise, maybe to microns, but accurate to millimeters, if not centimeters. And this is where if you calibrate, you'll really make that accuracy more and more better in real life.
Mm-hmm. All right. Thank you. Thank you for your question, Jean-Philippe. Let me see if I have another question. Okay, not now. I have some question then. What is the use case of the QR code that you talking about? I didn't get it.
So if anybody scanned it, you would find actually embedded that log data that you saw on the left. So that is just QR code. So it depends. If you scan it with your iPhone directly with like the camera app, it's going to try and call a phone number. Don't do that. I don't know whose phone number that is. But essentially what it actually is underneath is just a JSON, structured data. So that means that if I send that image into a Jira support ticket or to a client or whatever, they could just take a picture of it and scan it and get a whole JSON out of the JSON string out of the QR code. So it's just embedded encoded data in a more visual format that transports better as an image. If I were to just display the JSON string on our touch screen there, it doesn't take picture well. You can't necessarily copy and paste easy. Whereas with a QR code, you can easily just go snap and copy and paste your data where you need it to go. So it's just a way of really encoding our log data, and you can only store so much in a QR code, but it's honestly a lot better than before. to get as much data as quickly as possible from a machine into the hands of our customer success people and our application engineers.
Okay, but the QR code is pop up at the screen of the robot.
It would pop up on the screen of the robot, and that way you just take a picture of it and you have your log data instantly there.
Okay, yeah. Talk about log. I mean, how many data? How many? Like for example, the robot that you show us, like the one that looks like a dog.
Yeah.
How many data do you have each day for one robot?
So if you were to record it continuously, you have 5 high definition cameras on the robot itself. You have a camera on the hand of the robot. You have battery data, position data. You can attach extra sensors. So we attach humidity, temperature, luminosity, all these extra sensors on top of this. And you could then query those at hundreds of hertz if you want to, essentially. So you could create gigabytes of data per minute if you wanted to. You can create a lot of data really quickly. Another example, never mind the Spot robot, the Haloti robot, we had 3 4K cameras running at 60 frames a second, essentially. And that's gigabytes of data per like 30 seconds that you could collect if you really wanted to take your raw data. And so this often is a question when you're doing a lot of these edge applications, is where do you optimize your data? Do you take the raw and transport it right away? Or do you use some compute resources to downsample it at the edge and then only transport, your downsampled, smaller data, if you will? It depends. There's pros and cons to everything. I'll say right away that transporting 3 times 4K images is not a good solution, and doing some downsampling as quickly as possible in memory is a great starting point. But for other applications, sometimes it's just best, ping it out there and let the subscribers take care of the transformations.
Okay, cool. Thank you. Okay, let me take another look. Okay. I will continue with my questions then. Okay. But when you mentioned about Metabase, what is Metabase? Yeah.
Metabase, if I remember, their tagline, if you will, is essentially a business intelligence dashboard type thing and data versioning tool that makes it really easy, I find, for non-expert users to interact with data. So the first application I usually deploy it on is when somebody says they have an Excel file or a CSV file that they want to visualize as if you use it on a database. Metabase is able to bring those in and just display it nicely. And they also take approach where, and this is actually a very good approach from a data science point of view, is always go into your data with a question. It's sort of like, question-driven research, if you will. It's your hypothesis. And so Metabase lets you build up and sort of like automatically put together SQL queries based on natural language questions about my data, which is a lot of fun. And so it's just a really nice open source business intelligence, dashboard visualizer compared to Grafana, which is more on your monitoring and observability stack. So Grafana is really that real time, how many printers do I have running right now? Where are they located in the world? What's the max temperature, min temperature, all those real time metrics and, uptime and those types of things. Whereas Metabase is like, how many prints did I do over the last month? What is, the highest temperature over the past year? Those more business intelligence side stuff.
Okay. Oh wow. Yeah, I have to take a look at that. Okay.
It's really pretty. That helps with certain stakeholders.
Okay. Yeah. Okay. Cool. Okay. Let me see. I don't think we have another question, but I have a last one for you before we go to the end. You talk about CI/CD and how you deploy Docker images on robot or some kind of that stuff. How often you deploy like the new image or new code in the production?
Yeah, in production is an interesting one. So I'm going to use Aeon 3D, I think, as the example for this one. So with Baleno is really easy. We get to just spin up your container builds, and through the fleet management, we're able to select a certain number of printers internally as our alpha canary type printers. They got nightlies always deployed, latest master branch. Then we defined a certain set of printers as our beta printers, so those maybe got our latest stable release. And then only then would we start maybe rolling out to clients. And so we do like a rolling deployment where our clients that had the least critical applications, maybe they got the first wave of updates, and then slowly we deploy to more and more conservative clients at the end. I would say that we were deploying a lot of these robotics applications deploys to clients at most once a month in hardware type applications with running systems like this, to tell the clients that, hey, by the way, you have a new system that might change things too quickly. Maybe there's downtime, maybe there's things they just want. A lot of times clients in the hardware space, if it's working, they just don't want it touched. And so only during their next downtime would you then maybe roll out an update. Whereas internally, we were deploying software every day. We were pushing out the latest and latest releases, and that let us build up to, unfortunately, is bigger releases as you wait a month, maybe a quarter for like a big client release. But at least internally, we were able to test as quickly as possible and get those feature branches merged quickly. Same thing with Haloti, probably only once a month, once a quarter that we do big updates to clients. Patch fixes happened more regularly, but actual big feature updates that might change the behavior of a system, and that was a big one. If the behavior changes of the system, you got to really take a step back and say, okay, how do I educate my client that there's something that there's a different experience that they're about to get, and how should they approach that experience?
Okay, yeah. I mean, it's not it's not always easy to communicate with client, right?
No, and there's safety issues too. Like if something goes wrong, a 3D printer is an oven, so you have heated things, but a self-balancing humanoid robot, something goes wrong, it falls over and might hurt somebody. So you have to take a much more conservative approach when deploying to the real world.
Okay, cool. Yeah, I think I'm done, Yannick, with the question. I don't know if you have some for Nicholas.
Excellent. I have lots of questions that sprung in my mind while I was watching this presentation, but I will save those for the happy hour. That seems adequate at this time of the day. Nicholas, thank you again. Hopefully you'll be able to join us for the happy hour. And talking about the happy hour, let me remind everyone that it is right here at this URL. It's also a clickable link in the description of this video on YouTube. And in 4 weeks, what date would that be? We are going to have our next event. That is going to be on March 20th. That's the beauty of having a month that ends on the multiple of 7 boundary. So March 20th, our next event, and we don't have a number for this one yet. There might be a little trickiness going on with the number. You'll see. We keep that as a surprise, but stay tuned on Meetup and you'll know everything about it. Any closing remarks, Dirk?
But non, I just
oui, répète-nous tout ça en français. Là.
Oui, c'est ça. C'est que c'est ça, dans 4 semaines, on va déjà avoir notre prochain événement. Et comme toujours, on cherche des présentateurs. Fait que envoyez-nous si vous avez travaillé avec des trucs cool comme Nicolas, ou même si vous pensez que c'est pas très cool, mais si vous voulez quand même partager avec nous, ça nous fait toujours plaisir d'entendre qu'est-ce que vous avez travaillé dessus sur Python. Et je répète encore, restez, écoutez-nous de temps en temps sur tous nos channels de communication. Fait que on va vous envoyer tout ce qu'on va faire et tout ça.
Bon, c'est super. Au revoir tout le monde et on se voit le mois prochain.
Bye bye tout le monde. Merci.
Bye.